Okay, so last class we were, this is lecture 12. Okay, so last class we talked about singular value decomposition, the greedy algorithm for computing SVD, right? So we define singular value decomposition, and its properties allowed us to say that we can compute SVD by computing one singular vector at a time. And that's a remarkable property because we don't know how to handle multiple things, but we can compute one at a time. And for each one, we introduce a simple idea of applying the power iteration algorithm. Okay? And our goal today is to kind of understand what PI does. So when does it work, why does it work, and things like that. And then we'll finally end with some further remarks on when is SVD useful and things like that. And hopefully if we have time, we can start the next module. And just as a reminder, we also have assignment. So assignment 3 is up on course website. Okay? Alright, so just to recall, our goal was to compute, our input was a matrix X, which is some n by d matrix, and our goal was to compute argmax V, which is unit norm, and maximizes the length of X times V. Right, that's the first right singular vector. We want to compute that. Once we can do it, we can do lots of stuff. And in the end, we arrived at this power iteration algorithm. Right, so we said, start with V0, some initial vector, and for t equals 1 to t, u was x transpose times x times vt minus 1. Vt was u divided by 1. Okay, so this was the algorithm we ended up with in the last lecture. So there's a small difference here. I'm unable to load the previous one to show, kind of start from there, but the small difference from last time was that I'm normalizing the vector after each iteration. And the reason to do that is just like numerical stability. When you compute with numbers, multiplying by 2 to the 100 and dividing by 2 to the 100 is could be very fragile. Whereas if you kind of divide every time, then the numbers stay bounded and things might be nicer. Any questions about this setup? So that's the basic algorithm, and the idea was that they should converge to the top singular vector. Okay, and we also said that we are going to compute this just by matrix vector products and never compute a matrix product. So what can we say about this algorithm? And what we will show is that this indeed converges to the top singular vector as long as there is some noticeable gap between the top and the second best. Right? So we want to converge to the first singular vector, right? But what if sigma 1, the first singular value, is very close to sigma 2, right? So then what is top is not very clear. So you might need more number of iterations to converge. And that's exactly what happens. So let X equal u sigma v transpose be its SVD. And Suppose we have the singular values are sigma 1, sigma 2 all the way. You have some decreasing things. Okay, or the singular values. So here's a question. Is the first singular vector always unique? No, right? What if sigma 1 equals sigma 2? What can we say about the convergence of power iteration or any method in that case? What's the best guarantee that we can get? There's no single top singular vector there. There's a subspace of vectors which will all give the same maximum value for the in length of the inner product, right? So that's exactly what we are going to show. So suppose that let's say you go some number of steps, and at that point sigma k plus 1 is the first k are very close to each other, and the k plus 1 is less than sigma 1. So keep going along the singular vectors, singular values, until you see a 0.1%, an epsilon percent drop from the largest one, right? So in some sense, the first k, whichever this k are, when they're all close to each other, it's going to be difficult to identify the first one among this k. Okay. So what would be an ideal thing to conclude in this case? If I want a vector which gives me the largest inner product, what would be a nice conclusion to have? I know that the top k are very close to each other, and then there is a drop from sigma k to sigma k plus 1, all the way there. So what can I say in that case? Well, what happens is, let's say u equals span of first k singular vectors. And what we can say is that power iteration basically converges to something which is as good as any of the first k. We might not be able to point out which among this k is converging to, but that might be okay, right? Because all of those are giving you very high singular value in any case. So theorem, after t iterations, Vt is essentially in the span of that is Vt minus this is okay, so let me explain this statement. So it's saying, you're going to converge to some vector within the span of the top k singular vectors. There's a question, are we supposing this inequalities for sigma k and sigma k plus 1? Yes. So we're assuming the k is the index where there is a noticeable drop in the singular value.
Sorry, I meant to say
right?
why.
So if all the singular values, all of the singular values are exactly 1, then there's no notion of the top singular vector, right? So
Right.
any vector will do equally well. But on the
Sorry,
other
I meant to
hand, we
say
want to say that we can identify the top singular vector when there is some gap. If all of
okay.
them are the same, there is no notion of top, so it's not a very meaningful question to ask. So we're saying keep going among the singular values until you see a drop. Then we're saying we'll converge to something within the span of this top singular vectors. M something where any vector gives me a value which is very close to the top. Okay? Any yeah, I'm unable to hear you. I think you're muted.
No, can you hear me?
I can hear her.
Can you try talking now?
Can you hear me, Raghu?
Oh, I think he cannot hear us.
I'm not sure. My sound is down. Weird. Hold on. Oh. Okay, I can hear you guys. Sorry.
Hello?
Yeah, I can hear you now. The
Oh,
speaker
okay.
somehow was set to something else. Sorry about that.
So
Okay.
I was just asking, why are we making the assumption that sigma k is greater than 1 minus epsilon times sigma 1, and then the same for the next?
So it's not really an assumption, right? Basically, it's saying, the singular values are like, let's say this is sigma 1, let's say I'm trying to plot them, right? And they're decreasing. Okay, so these are the, this is sigma 2, sigma 3, and so on. And what this is saying is, if all the sigmas are actually the same, if there is no like a single top singular value, all of them are, let's say, 1 in magnitude, then we might not really converge to V1 because there is no real difference between V1 and V2. Both of them get the same length, right? And saying, okay, so in that case, we can't really say we converge to the top, but what we can say about the power iteration is keep going like this until you see some drop in the singular value. So this one is maybe 0.99 times sigma 1. Alright, so keep going on this sort of downward trajectory until you get to 0.99 times sigma 1. And the claim is that the power iteration after some number of iterations converges to something which is close to what's happening in this top k things, whatever the k is. Does it make sense?
Yeah, it does. Thank you.
So, so let me say the general thing and then we will focus on, let me not erase this, and we'll focus on the more special case. Okay. So after t iterations, we know that Vt is essentially in the span of the top of the first k singular vectors, whichever get a value which is 1 minus epsilon times sigma 1. Right? And depending on epsilon, that kind of determines how many iterations we need to run. Okay, and there is one more thing here. So as the number of iterations increases, the gap, how far you are from the span of these vectors. So let's think of this as u, then Vt is basically very close to this subspace, and this length is decreasing kind of at an exponential rate depending on the gap between the top singular vector, like depending on the threshold epsilon you're setting, it's decreasing at an exponential rate. Okay, so that's the most general statement that you can say about power iteration. Let's look at a special case. Suppose sigma 2 is less than 1 minus epsilon times sigma 1. So this is saying, actually, you know what, let's say that there is a noticeable gap between the top one and the second best one. Okay, so in this case you can conclude that after t iterations, the distance between Vt and V2 first singular vector is at most if indeed there was a noticeable gap between the first and the second, then you are kind of converging to the true first singular vector, where the number of iterations you need kind of depends on this gap. And this is something that shows up a lot in many matrix algorithms, especially to do with singular values, eigenvalues, where your convergence bounds depends on the gap between the top singular values, which kind of intuitively makes sense, right? If sigma 1 is equal to sigma 2, then you cannot pinpoint a single vector which achieves the maximum. There are two things, and anything in the span will also do equally well. Okay, any questions about this statement? Yes, no? Okay, all right, so what I'm going to do in this lecture is only prove this special case, and the analysis for the general case where you don't necessarily have a gap between the first and the second, but there may be a gap lower down, is very similar to the special case analysis that we're going to do. Right? You just have to kind of essentially replace wherever we use 2 to k, and you'll get this more refined statement. Okay. All right, so let's try and analyze why this is happening. Why is this converging so fast? So in particular, what this is saying is okay, so there's one more aspect here, right? So which is that your convergence depends on how close your initial vector is to the true singular vector. If you're starting with something close to the true singular vector, then you're converging even faster. Whereas if you're like if this inner product is 0, if you're starting with something perpendicular to the true singular vector, then you don't make any progress. Okay, so it's kind of a subtle thing, right? And how do we fix this? Why isn't this an issue? How can I make sure that I'm not orthogonal to the true singular vector, right? And if I'm perpendicular to it, I'll stay perpendicular to it. I won't make any progress. So what's the way around that? Any suggestions? How can I get at least some non-trivial correlation with the true singular vector for my initialization?
Assume V0 is not perpendicular to V true, or like set V0 so it's not perpendicular.
Yeah, but how do I do that? Like, I'm writing down the full algorithm, right? How do I do that in my algorithm? So what's the natural thing to do to fix this? Like, imagine, you're actually implementing it. What would you do?
You initialize it to like a fake one, maybe?
To a what?
A fake one, you assume that there exists one.
Yeah, but how do I, what's actually going to go into my code? What happened here? Okay. Hold on, let me. Yeah, go ahead. So I think you're on the right track, but I think that actually there's a simpler solution. So basically, all we want is something to be not perpendicular to V true, right? And being perpendicular is a sort of a very rare occurrence. It's kind of a very rigid constraint. Right? I'm not sure what's happening today with this app. Anyway, it's not letting me copy, so let me just write it down again. So V0 is something, and for t equals 1 through t, we set u is x transpose times x times v, and then v was u divided by over. Okay. So what should I do for initialization, right? Well, all I need is the inner product to not be 0, or like, something non-trivial, right? And you can easily ensure that by picking a random unit vector. Whoa. What happened there? Okay. I need to contact the developers about it. Anyway, so if it's a random unit vector, then it's kind of unlikely that you'll actually be perfectly perpendicular to some fixed vector. Okay? And you can show that with high probability V0 is random, then this value between V true is about 1 over square root t. Okay, and that's a theorem. Okay, like basically you'll expect correlation about 1 over square root t. Okay. So as a corollary, what we can say is that if sigma 2 is less than 1 minus epsilon times sigma 1, then after t, which is something like, let's see, you have to kill the t. Okay, so basically after something like log of d over delta, right? So I'm setting t to be 1 over epsilon times log of d over delta, so that this whole thing becomes delta. And after these many iterations, you arrive at a vector which is delta close to the true singular vector. Okay, so you are converging very fast, and the speed of convergence depends on how close the first two singular values are. Okay, and you can, as I said, you can generalize this to the case where maybe there's no gap between sigma 1 and sigma 2, but there is some gap down the line. Maybe the 100th singular value is less than sigma 1. You can say that you converge to something which is in the span of the first 100 in that case. Okay. All right, so let's do a quick demo of this to see what's happening. Hold on. Okay, so now let's do a quick demo of power iteration on some small matrices, and let's see how its behavior changes with changing gap between the first and second singular values. And you can see here that our bound says that, you know, as the gap sort of increases, as the ratio between sigma 1 and sigma 2 gets bigger, the number of steps needed should get smaller. So if they're very close, then the number of steps you need to converge to the top singular vector should be high. Okay, so let's go to the workspace, and here we are. So here's a simple implementation of power iteration. You know, you just start with an initial vector, you multiply that vector in each iteration with x and then with x transpose, and you normalize. Right? This is just 3 lines of code implementing the power iteration. And now don't worry about the momentum method, we'll come to that later. And let's check how power iteration performs on some matrices. So I'm going to choose a 1000 by 100 matrix here and run it for 1000 iterations. And I'm going to first start with a random matrix, random n by d matrix. And for a random n by d matrix, the gap between the top 2 singular values is not too big. So we won't really see a difference in convergence to the top singular value or singular vector. So let me create an artificial gap between the top 2 singular values by bumping up the top singular value a little bit. And don't ask me exactly why this would work, but basically what I'm doing here is I'm computing the top singular vectors using the inbuilt function, and then nudging the original matrix by adding a small multiple of u1 v1 transpose, so that the top singular value increases a little. So the top one increases, the rest stays the same, so you're increasing the gap. And this number a qualitatively controls how much gap there is. So, and then I just run power iteration for all of these things, compute the true top singular vector using the inbuilt implementation, and check the distance. How is the distance between my vector v in each iteration changing with the true top singular vector? And one caveat here is that when comparing the distance, we need to be a bit careful, because both the top, if v1 is a top singular vector, then v1 and minus v1 can both be considered top singular vector. So your power iteration could converge to either one depending on the initialization. So for that reason, I compare the absolute values just to get around this sign issue. And here you can see that as the gap increases, the number of iterations is much smaller, is decreasing. To get a desired error, the number of iterations required is very small. And you can also see that the distance to optimum, the convergence to the optimum, has this line like plot here. And you might wonder why there is a line, but remember that this is a log plot. So I'm plotting log of the error. So when I take the log, and if it is becoming linear, that means you're having exponential decrease in the error. Okay, and it's kind of clearly evident in this diagram when you plot log of the distance to optimum. And the rate and kind of the slope of this line is determined by the gap as evidenced here. Okay, and you can play with this values by yourself to see what happens for other values of alpha and so on. There will be fluctuations because of the randomness of x, 0, but by and large you should see some trend like this. Okay, now let's go back. Alright, so what we are saying is that you will converge to the top singular vector up to this guy. So I need to refine this statement too, which is to say that minus the projection onto span of V true Vt is going to be at most delta, right? So essentially I'm going to converge either to the true singular vector or to the negation of the true singular vector. In either case, the projection onto the span of your true singular vector is going to be almost a full vector. Okay? So remark V r minus V unit of S V. Okay, so let's try and analyze this, right? So why is this true? And the proof is pretty much basically how we arrive at the algorithm, right? So this is one of the cases where if you didn't know how to analyze it, you wouldn't have even come up with the algorithm. Okay? So let's go back to the idea behind power iteration, right? So what was the idea? So suppose that V1, V2, all the way up to Vp were the singular vectors. Okay? And in last class we showed that X transpose X. What was this matrix? This was a matrix which had a very nice expansion in terms of these true singular vectors. Okay? So I'm using superscript for the true ones and the subscripts are for the iterations that come out of the power iteration algorithm. Okay? And so if this is the update, and let's say V0 is our starting point, and I'm going to write it in, so let's go back to what the algorithm is. So we have V0 and V1 is X transpose times X times V0 divided by okay, and then we have something iteratively like this. Vt was X transpose X times Vt minus 1 divided by the norm. Okay, so we are dividing by the norm of the vector each time, right? But I can simplify this and still write Vi directly in terms of V0. And how can I do that? What is each iteration really in terms of the action of X transpose X and V0? Let's see what happens after second step, right? V2 is X transpose X times V1 divided by some norm, okay? Which is just X transpose X times X transpose X times V0 divided by some number. Okay? So, which in turn is just X transpose X whole squared times V0 divided by something. And what's that something? Well, we know that the final result is a unit vector. So, it's just going to be this. Okay? So, an equivalent way of writing the power iteration is saying that you're just looking at X transpose X applied T times to my starting vector V0 and then normalizing the whole thing by the norm. Okay? Does this make sense? So we wrote it iteratively, but I'm saying we can write it even more succinctly in this way. And what we'll try and do is to show that basically when you look at this expression, the numerator is a vector whose inner product with the top singular vector is always kind of staying is getting closer and closer to the top singular vector. Okay? So how do we do this? We'll do this in by analyzing the numerator and denominator separately. So let's look at x transpose x to the t times v0. I want to understand how this changes the inner product with the actual true singular vector. And how can I do that? Well, so let v0 be write v0 in the basis of the singular vectors. Okay, suppose I write it in the basis of the singular vectors. Then, and maybe I even have v0 is some c0, some c1 times v1 plus c2 times v2 plus so on, cd times vd. Okay, and we also know what x transpose x is, right? It was this matrix exactly sigma I squared times vi. So I want to claim that these two tell me exactly what the inner product of x transpose x and v0 is. Can anyone tell me what's the expression that I would get if I write down this matrix vector product? How would it change the coefficients of the vector in this expansion in the basis? So I have a matrix here, I have a vector here, and I'm asking what's the matrix vector product like? What is it doing? Any guesses? Vi becomes inner product. Okay, so let's write it down. Right. This is our matrix, and I have some crazy or somewhat even maybe messy looking expression. Okay. So when I expand this out, what would happen? Which terms would survive and which terms would disappear? Any guesses?
Any I not equal to j is going to go to 0 because they're orthonormal.
Right, exactly. So the VI's are these two singular vectors are orthogonal to each other, right? So when I expand them out, any I not equal to j would be 0. So by orthonormality of the V's, the inner product Vi comma V equals 0 if I not equals j. Okay, so the expression then is just Ci times sigma I squared times Vi. Okay, so basically what it's saying is, if I write down V0, my starting vector in the basis of the singular vectors, then after each application of x transpose x, I'm multiplying the coefficients by sigma I squared. That's the only change that's happening. The Ci's are as they are. I kind of just bumped up then, multiplicatively by sigma I squared. Bumped up or bumped down, but multiplicatively change them by sigma I squared. Okay. Now what happens if I iterate this? So what does this tell me about the tth iteration? So what would I get here? How are the coefficients changing as I keep repeatedly multiply x transpose x? Well, I can use the same expression again, right? The CI's now are maybe like CI times sigma I squared. And if I do the same calculation again, what would I get here? What are the new coefficients? What would the new coefficients be? Sigma I to the 2t times Vi. Right? Okay. So each time I do this operation of multiplying with x transpose x, the coefficients change by multiplicative sigma I squared for each I. Okay. So after t iterations, what I have is this expression for the vectors that are showing up in the power iteration. Okay. Alright, so now if we go back to the power iteration, so we said you have to the t times v0 divided by to the t times v0. Okay, so this was what our algorithm was doing. And we also have some intuition now for what is happening in terms of the basis of singular vectors. Okay, so now let's analyze what happens to the numerator and denominator separated. Okay, so if I want now to compute the projection of my Vt to the span of the first singular vector, what is it? Any guesses? So I'm giving you its expansion in an orthonormal basis, right? And I'm asking you what's the projection onto the first vector in this orthonormal basis? What is it exactly? Any guesses?
C1 times sigma 1 to the 2t times v1.
Exactly, right? So this is just C1 times sigma 1 to the 2t times V1. I mean, I wrote down the entire basis expansion, right? So the first coordinate of the first coordinate of the projection is exactly this much. You have a normalization term though, which is whatever this denominator is. It seems like a slightly messy thing, but we'll get to that shortly. Okay? So, I wanted to control how far my Vt was to the true singular vector. Right? What is this norm squared then? Maybe even, let me write it without the norm squared. So what's the difference then? It's just, you subtract the 2 out. What I get is all the things except the first singular vector. Okay? I know exactly what Vt is. I know what the projection is. You take out the first singular vector out. So the difference is everything except the first. So note that the summation here is starting from 2. Okay? And we also know that the VI's are orthonormal vectors, so they're perpendicular to each other. So what can I say about the norm of this distance to the true singular vector? What is an expression for the norm of this distance to the true singular vector? Well, I have given you the expansion. We have arrived at the expansion in an orthonormal basis, right? Because the VI's are orthogonal to each other, orthonormal to each other even. So what's the length of this vector in terms of the coefficients? Well, first the scalar stays as it is, let me just copy that. But what's the length of this part? Any guesses? So we have a vector and its representation in some orthonormal basis, the VI's. So what's the length of the sum? Okay, so maybe okay, so let me ask a question. What's the length of, let's say, lambda 1 times v1 plus lambda 2 times v2 plus okay, so if the VI's are orthonormal, what's the length of a vector which is a linear combination of these orthonormal vectors? I tell you the coefficients are lambda 1, lambda 2 up to lambda d. So what's the length in this case?
Is it the sum of lambda 1 squared plus lambda 2 squared all the way to lambda d squared?
Yes, exactly. So it's going to be lambda 1 squared plus lambda 2 squared plus lambda d squared. Right, because it's an orthonormal basis. So it works just as if, those are the coordinates of the vector. Okay? So what I end up with then is summation I equals 2 to d of ci squared times sigma I to the 40. Okay? Alright. And by the same logic, we can also write down an exact formula for the denominator. Right? So let's look at the numerator, is summation I equals 2 to d of ci squared times sigma I to the 40. And the denominator, what is that guy? So the denominator, by denominator I mean norm of x transpose x v0 squared. So what is the denominator? If I use the same logic, we also have an expression for what this vector is, right, in an orthonormal basis. So the length is going to be, so what should the length be here? Well, I'll get the same expression, but starting even with the first coefficient. So let me write that maybe properly. Okay. So the distance to this first singular vector is the ratio of these two quantities. Okay. And the difference is that the numerator does not have the contribution coming from the first singular vector because we subtracted it out when we took out the projection. Okay. Any questions about that? So summary, distance of Vt, Vt minus the length of the projection onto V1, which is the distance to V1 squared, is this ratio. Okay, and we need to control this ratio. So essentially what happens is that, going back to our intuition, we said that we expect when we take higher powers, the smaller singular values to decay much faster than the first singular value, right? So the ratios from 2 to d, the singular values from 2 to d, they will be decaying much faster than the first one. So you would see a gap. Let's take a 5-minute break, and when we come back, we'll analyze this expression and get our bound on how fast power iteration converges to the top singular vector. Okay?
This meeting is being recorded.
Okay, so I fixed the code. So let's now look at what happens to the power iteration. In the same setup as before, we have n, which is 1000, d is 100, t is 100, and I'm generating a random matrix, okay, and then making it a little bit low rank by adding a rank 1 component, right? Some multiplier alpha, whatever that is, times a rank 1 matrix. Okay, and you can see that as I increase or change this 0.01, how much contribution the rank 1 part makes increases or decreases. And if it's 0.01 here, you can see that the power iteration is kind of having this sort of slow convergence, right? It's taking many iterations to get to a point where the error is small. But what if I make it, let's say, 0.1 even? You can see it's much faster. And if I make it 0.1, it's even faster. If I make it like 10, it's just like almost perpendicular. In a couple of iterations, it's converging to the true value. Okay? And what this alpha determines is the gap between the top two singular vectors. If I start with something very small, the gap is very small, so it takes a long time to get kind of small convergence. Okay? So it's kind of nice to see that this plays out even for small size matrices. The bounds that the theory is saying is actually what we are seeing in these plots. All right, so let's go back. And the mistake from earlier was I need to account for converging either to the true singular vector or the negatives of the singular vector. Okay, and here okay. So coming back to the analysis, we are in this situation where we have some kind of control on what the distance to the true singular vector is. Okay. So how can I proceed now? Any guesses? Okay, so our goal is to say that this number, the distance, is actually small. It's decreasing as you run for more and more iterations. Right? So what can I do to do that? Any guesses? Well, let's look at the numerator, right? So it's summation I equals 2 to the d sigma I squared, ci squared times sigma I to the 4t, right? But what do we know about all of the sigma i's but for the first one? What's an upper bound on them? Right? So we know that sigma 2 is at most 1 minus epsilon times sigma 1. Right? That was our assumption. Okay? So let me just plug that in. So I know the numerator is at most ci squared times 1 minus epsilon times sigma 1 whole to the power 4, which is okay. And what's an upper bound on this quantity? The sum of squares of the CI's, except for the first one. What do we know about that? Well, we chose our V0 to be a random unit vector, right? So its length must have been 1. That means that sum of squares of the CI's was 1. So this is less than or equal to 1 minus epsilon whole to the 4t times sigma 1 to the 4t. Okay, so we have some upper bound on the numerator. The numerator is in fact, decreasing at this rate. So are we done? What do you think? Yes, no? Well, it's not necessarily, we are not necessarily done because maybe the denominator is also decreasing, right? So the only difference between the two is starting at 2 versus starting at 1, right? Meaning you're taking the contribution of the first singular vector or not into account. Okay, so we also have ci squared times sigma I to the 4t. Okay, so let's forget everything else. I at least know this is as big as the first term. Okay, there are a lot of terms here. I'm going to ignore all of them and just look at the first term. It has some contribution. So therefore, the error is at most okay. That's pretty much it. No, we are basically done, right? We have the ratio, the error is at most 1 minus epsilon to the 4t divided by c1 squared. But what is c1 in terms of the starting vector and v1? So my claim is that we were writing V0 in the basis of the singular vectors. So each coefficient in this basis is exactly the inner product of the basis vector with the vector that we are expressing it in the basis. So we just get is at most divided by V0 comma V1 squared. Okay? That's the theorem, right? So it's saying that the error is at most 1 minus epsilon to the 4t divided by this starting inner product square. Okay? Any questions about this?
Wait, how did you calculate C1 again?
Say that again, sorry?
Like how do you know C1 is the dot product?
Oh, okay. So let's go back to what C1 was, right? So we wrote V0 in the basis of the singular vectors. Right? And this is an orthonormal basis. Okay? So, you know, if I take V0 comma V1 inner product, what happens? All the other inner products except the first would disappear. Right? And because, you know, they are all orthogonal to each other, and the first one would survive. So I would just get C1, V1, V1, which is 1. Okay? Does it make sense?
Yeah.
So in general, when I have an orthonormal basis, you can play with the coefficients quite a bit. Like, you know, when I take the inner product, I get the coefficient in that basis. Okay? So let's summarize what we did. Summary, let me write it in words. Basically, power iteration converges to the true singular vector at a ratio at rate something like 1 minus epsilon to the 40. Okay, so basically, you know, you need something like so to get error delta, we need roughly okay, and everything that we did will also, you know, you just have to stretch the proofs a little bit to get the more general statement I mentioned at the beginning, when there is no gap maybe just between the first and second singular vector, but there's a gap further down the line. Okay, and you can actually see it even in code if you just write it down, and if you go back to the workspace, which I'll share, and change k, you'll see that it doesn't work as well as when k is 1. You have to be a bit careful in how you define the distance. You'll only converge to something in the top k singular vector space instead of the top one. Okay? Alright, so let me now finish with some important aspects or features of the power iteration. Okay? So the algorithm is extremely simple, right? But it's also very, very important. And the reason it's so important in data mining is the following. So if you look at the iteration, what kind of access do you need to run the power iteration? So I'm trying to compute the first singular vector of this matrix X, right? But what kind of access do you need to run the power iteration? Do I need to know the entire, like, you know, write down the entire matrix in main memory or something? What's the minimal requirement or what is sufficient to actually run the algorithm? Any guesses? So we really only need the ability to compute matrix vector products, right? That's it. Okay. So imagine someone didn't give me what x was, but he gave me a function call, like an oracle, an implementation, which whenever I give it a vector v, it outputs x times v. That's all I have access to. Okay, I can still run power iteration. Right? So to implement it, we only need ability to compute matrix vector products. Okay, isn't that cool? Like, I only need to compute matrix vector products to run the power iteration and find the first singular vector. Right? So basically, I need to be able to compute x times v and x transpose times u. Can you think of a scenario where this could be very advantageous computationally? Any suggestions? Just think of a scenario where maybe writing down the whole matrix is hard, but not hard, is expensive, but computing matrix vector products is still easy.
The matrix is sparse.
Say that again?
The matrix is sparse.
When it is sparse, you said?
Yeah, that's what I'm thinking.
Yeah. So, well, when it is sparse, we can still do something. But let me think of when it is sparse, I can still write down the entire matrix in my memory, right? And I can also compute matrix vector products with equal sort of advantage. Sparse case, you can do this, but to push it up a little further, what if I have a product of matrices? So I give you as input, and let's say, x1, x2, x3, and I ask you to compute first singular vector of x1 times x2 times x3. Okay? So I have these matrices x1, x2, x3. I'm asking you to take the product and then compute the first singular vector. Now, do I have to compute this matrix product? No, right? Because if I ask you to compute x1 times x2 times x3 times v, I can use associativity. Right? So I can compute the singular vector of the product of matrices without even ever having to compute the product. And this can be really important in when you're implementing these algorithms, right? Because computing matrix products is very expensive. And going back to the point that Katie was raising, if each of these xi's is sparse, it's not necessary that the product is sparse. I could have sparse matrices whose product is dense. And in that case, I would be in deep trouble. Okay? Whereas sparse vector products are easy to compute. Okay? And this is very crucial, if you think of matrices like that show up in the Netflix challenge that I mentioned at the beginning, right? It's a huge matrix. Even to write down the matrix is like 8 GB of data. So you have to be you have to exploit all these things, and you can exploit, and people do exploit all such tricks. And there are streamlined applications in almost any numerical analysis software like MATLAB and NumPy, where you can actually just provide a handle which computes matrix vector products, and that will implement all the other optimizations and give you back the first singular vector. Okay. In fact, when I was in grad school, I had to dig up some Fortran and so on to figure this out for one of my research projects. Okay, so the second thing I want to say is look at the speed of convergence. Okay, look at the speed of convergence in terms of the gap between the first and the second singular vector. The speed was something like, let's ignore the dependence on the dimension and the final desired error, but the convergence was basically 1 over epsilon. If the gap was very small, then you needed many more iterations to get a good guarantee on convergence. Okay. Have you seen this 1 over epsilon before? Any suggestions? You know, we saw something like this before. And I'm asking, can we do something better than 1 over epsilon? Is there hope for beating this 1 over epsilon style convergence? What do you think? Does this ring any bell? No?
Was this gradient descent?
Yes, it's very connected to gradient descent actually. And when you think of gradient descent, we also saw a much more sophisticated form of gradient descent, right? Which got 1 over square root epsilon convergence. Okay. So we can actually do something better, which is accelerated power iteration. I mean, it's not really a technical term. We can in fact design an algorithm. There are many forms for it, which gets convergence 1 over square root epsilon. Okay, so it's quadratically faster than the plain power iteration that we just saw. Right? You can run, can get significant savings. So to get error delta, need okay, so there are faster ways of it's kind of a variant of power iteration where you don't change too much, but you still converge fast. And it's very similar to Nesterov's accelerated gradient descent method or momentum based methods. Okay, so if you want to look up these things, there's something called Lanczos iteration, which achieves this 1 over square root epsilon. The other thing which is, is to think of it as power iteration plus momentum. Okay. So remember when we talked about gradient descent, we said we can do an accelerated gradient descent which we somehow take the previous history into account, right? And in power iteration, we are ignoring the entire previous history, right? So you can change it to say something like Vt is So these are not the actual updates, but like, you know, something almost exactly like this. So you update just as before in the power iteration, but then you add a term which depends on the previous iteration, right? Even in gradient descent, we said that when you take that into account, you can speed up the convergence. And the same thing can be made to work for power iteration as well. You have to choose beta much more carefully, but you can make it work, and it converges in 1 over square root epsilon iterations, which is very cool, right? Okay. So the other thing I want to say is, okay, so PI was for computing top singular vector. Okay. There's a question, beta is constant in every iteration. In the simplest form, you can try to take beta to be constant, but basically I think you really have to tune it a little, like, you know, maybe initially choose it to be constant and then kind of adjust it a little in terms of how aggressively you take the previous history into account. You know, just as for accelerated gradient descent, you had to play some tricks to figure out this beta. Okay. So I'll post a reference to a paper, this is not that old. This power iteration plus momentum term was kind of only analyzed relatively recently. But Lanczos is very old, and there are very good implementations of that in all numerical analysis software. All right. So the other thing I want to say is that everything we discussed so far is for computing the top singular vector, right? But what if for some reason someone comes and says, okay, tell me the bottom singular vector. Tell me the smallest singular vector. What would you do? Any guesses? Okay, so to make things easier, let's say I tell you that X was a square matrix. And I want you to compute the bottom singular vector of X. What can you do? Any guesses? Square symmetric UN. Well, you know, if I look at a big number C times identity minus X, okay, then the singular vectors shift and they'll flip. So like you can play all these tricks to try and compute the top. You can use the same kind of routine to cut the bottom one. If I just subtract identity minus X, if I compute that and compute the top singular vector of that, I'll get the bottom singular vector of X. So you can play all of these tricks. Can be top of this is bottom of X. Okay. So one last thing. Suppose X was had singular vectors 1, 0.99, 0.98, so on. Okay. So now if I run power iteration, the convergence is going to be slow, right? Because the gap between the first and the second is very small. So the gap epsilon is like 0.01. there's only a 1% reduction from the first to the second. Right? But on the other hand, the singular values of x minus ci are shifts of the so let's say these are all 0.99. So I'll put this in quotes because it's not always true, but I want to teach you some of the tricks that people use to speed up the convergence of the power iteration. So when I subtract something minus the identity, the singular values kind of shift a little, right? But the singular vectors don't change. Basically, you essentially just kind of replace. You could potentially replace u with y. The singular values appropriately. So if this is something that I can do, then what can I do? Any suggestions? If you want to speed up the convergence of power iteration, is there something to gain by looking at x minus ci for some c? What do you think? Well, if I look at x minus 0.98 times identity, has singular values that are 0.02, 0.01, 0.01, so on. Okay, so by shifting the matrix, I made the gap between the first and the second much higher. Right, so here the gap was only 1%, whereas here the gap is 50%. Right? So, again, what I'm saying here is not rigorous. Things don't shift exactly like this when you talk about singular values, but you just have to take a slight leap, and if you start talking about eigenvalues, then they do shift in this way. So people often do these tricks, and in fact, when you look at numerical linear algebra software, they do implement all such hacks to get the fastest convergence to the top singular vectors. Basically, you want to shift something so that you have the maximum gap between the first and the second singular value. Okay? Alright, so that's all I want to say today, and in the next class we will start with a different topic after a quick summary of what we did for singular values. That's all for today.